on maybe Thursday, Friday. I can't remember. Sometime Thursday or Friday. And I had a lot of things to do before I left, including getting a visa for Brazil, which didn't happen until less than 24 hours before the flight. Yeah, but I did have time to think about what this could be, and then I thought maybe let's just pick a topic that everyone can contribute to a little bit. And so this is not about me telling you anything, it's more about me mediating the discussion. I will provide a few slides for gentle entertainment, and there will be a quiz that will be conducted during the presentation. But otherwise, I hope that everyone can provide the content as much as possible. So the talk is divided into these sections. First, we'll identify what it is to be a hybrid magnon. Second, we'll think of different physical manifestations of hybrid magnons. We can talk about functionality for either technology or science questions. And then we ask, what are the open science and technology questions about hybrid magnons and how to realize them and how to measure them? And then related to that, we can ask what experiments do we still need to do in order to make things work, and what theory do we still need? So the first question is, what is this hybrid magnon? And we've already had a couple of explanations of hybrid magnons this morning from the last two speakers. And I'm sure that we will have more, including tomorrow, where the title of the talk is essentially this. But we can ask first about hybridization, and hybridization is a concept that has been known for thousands of years. And, the ancient Greeks thought of this minotaur, and the minotaur is, of course, a combination of a man and a bull. And they also thought of this chimera. The chimera is a combination of three animals, a lion, a goat, and a snake. Okay. And then I thought, well, okay, we've got all these examples from ancient Greece, but I'm going to Brazil. And when I think about Brazil, I realized there are a lot of hybrids here too. A lot of the animals in Brazil are kinds of hybrids. So there's this animal on the left that is very common in Canada where I'm from. And if you mix this animal, the beaver, with, say, a Shetland pony, what kind of animal do you think you would get? You get this funny thing. And for most of us, this is some kind of rodent, but I guess if there are Catholics who respect Lent, then this animal is a direct equivalence to this, at least according to the Catholic Church, where you're not allowed to eat meat, but you can eat fish, and you can eat capybara. Okay, so there will be some more quiz questions throughout the talk, but I want to open the discussion about what physical manifestations we can have for hybrid magnons. And just to nucleate the discussion, I started listing a few here. If people think they're invalid, they're welcome to say so. Or if they think that some others are another example that they haven't thought of, they can say so. So we've already heard about magnons hybridizing with photons, and then this coupling can be either coherent, quantum, or incoherent, and we've had some debate about what that means, coherent or incoherent, or quantum or classical coupling. We can couple magnons to phonons in a number of different ways. So classically, we can have magnetostrictions. You can change, say, the lattice constant depending on the magnetic phase of a system. Or you can induce strain in a magnetic system and change the exchange for neighboring spins. And that can induce a magnetic phase transition. You can also imagine coupling to quanta of excitations through the magnetic system, and that might lead to interesting new phenomena. We can also couple magnons to single spins, and we've already heard a bit of that. And they can mediate effectively interactions between those single spins. Magnons can also couple to electronic bound states, and I'll talk a little bit about that tomorrow in my talk, Wednesday in my talk, where the magnetic texture that you get at a domain wall can induce a special type of bound state if you have a Dirac-like electron spectrum. So on the surface of a topological insulator decorated with magnetic moments, if the magnetic moments have a difference in their orientation along a domain wall, you get extra topologically protected bound states, Jackie-Vreby bound states. And then you can think of different ways of understanding this. So those electronic bound states can be treated as quantum mechanical, while the domain wall is treated as classical, fixed in space. But you can also think of magnetic excitations that are quantum mechanical, like spin waves. So those are delocalized in space because they are like the superposition of creating a spin flip at all points in space in the crystal. And you can think of localizing electronic states at each of those spin flips in superposition, and that creates a kind of other exotic beast that looks like a kind of quantum hybrid between electronic and magnetic excitations. And I'll talk about that a bit on Wednesday morning if you want to know more. You can also hybridize different Magnon modes to get interesting dispersion relations, and I think we heard a bit about that from Michael's talk, where he talked about generating a little minimum in the dispersion by hybridizing two different Magnon modes of different character, and we can get different functionalities from that kind of thing. Another thing you can do is hybridize single Magnon excitations with two Magnon bound states if you have a spin non-conserving perturbation, and that can lead to interesting new functionalities. My student Ivan will talk about that during his talk. Are there examples of hybrid Magnon systems that aren't here that you would like represented on the list, or that anyone has? Sorry? Well, you should use the microphone and explain what you mean.
I mean hybridization of a magnon with a qubit,
yeah.
Unless you count qubit as an electronic bound state, which in some...
Oh, it could be, I guess, but I guess that's a very good example, yeah. So for me, a single spin is a qubit as well, if it's a spin 1/2.
Yeah, but not every qubit is a single spin, right?
That's absolutely right, yeah. But every qubit is a two-level system. Last I checked.
Kind of, yeah.
Well, you should give it another name. It's a qdit or a qnit.
Yeah, but even for a qubit, you have the third level, which
of course,
you usually
that's
use
physics.
But okay,
the distinction between physics and math, yeah.
Yeah, we are slowly going to semantics, which we should not be doing.
Oh, no, I like semantics. It's entertaining. So are there other examples of hybridized systems? Magnons hybridized with something? I think we're going to get through this pretty quickly. Poliana.
I don't know. This is something I was actually discussing with Dennis, and we were thinking about could you have Magnons in systems hosting Majorana fermions?
Probably. I don't see why not.
Yeah.
And what would is there a specific aspect that would be interesting there?
Yeah, I don't know. Because Majoranas don't couple to...
But Majoranas
yeah.
want a specific range of magnetic field for
exactly.
chemical potential, right? So you could have the presence or absence of a Majorana depending on the presence or absence of a particular magnetic excitation, maybe? I think that's a good idea, no? Maybe exotic.
Well, you mentioned the Jack ribeye or whatever you call that. Yeah, that in a way that's related to Majorana, right? So I guess it is probably true. I mean, this BS that people say Majoranas do not really couple to things. It's not. Yeah,
no, it's a zero mode in the same way. That,
So
Majoranas are zero modes. It has the same origins. Mm-hmm. Okay. If there are no further questions about this or comments, I'll go to the next quiz question.
I'm not sure. This may sound dumb, but what about plasmons? And those are like a collective already excitation and Magnons.
I see. So you want to hybridize the hybrid. Yeah, I mean, if you can couple Magnons to phonons, you can couple Magnons to electrons. Why not couple them to plasmons? Sure. And everything.
Everything. Polaritons or whatever.
Yeah. Yeah. Please.
Wait.
So I saw this paper long ago of people using like magnons to sense gravitational waves and potentially even gravitons. So do not know much about it, but if anyone in the room knows a little bit about this, including you, that would be interesting to.
So I don't know about using them to detect gravitational waves, but I think it's actually quite common for people to think about that in the context of dark matter detection.
Well, that's like through the axionic term, but what I'm talking about is slightly different. Yeah.
I don't know anything about detecting gravitational waves with Magnons specifically. So is the idea connected to looking at the change in the effective strain of a sample?
Correct.
And that changes the character of the Magnon somehow?
That's correct.
And you think that could be sensitive enough to detect gravitational waves?
I'm not claiming anything. I'm just, but that's what they claim. But yeah, I was just wondering. Now I should apologize for bringing that up, but
no, this is the point of the
right,
open discussion,
like,
right?
Yeah.
So it's an interesting idea. I don't understand off the top of my head why that's a particular good way to measure a gravitational wave. Certainly, Magnons are sensitive to strain, but so many other things are as well. And Magnons are usually short-lived excitations. I don't know if I would want to use a short-lived excitation for that. If you could make a Magnon live forever, maybe it's a good idea. Okay. So the next quiz question, again, we're on the topic of hybrid Brazilian animals. So if I hybridize these two things, what do you think of?
Is it parrot? Parrot?
Sorry?
Parrot.
Mr. Trump. I'm Canadian. I don't have a president. I have a prime minister. And his name is not Trump. It's okay, sir. I didn't introduce myself. I'm Bill Coish from McGill University in Montreal, Canada. It's a nice city in Quebec. We don't have a president, but that's okay. So what kind of Brazilian animal do you think of when you see these things?
Bird?
Sorry?
A bird?
A bird. What kind of bird?
You know, like a parrot?
What kind of? Papagayo, yeah. So which in English is a specific one? Yeah, there's one that eats this cereal. If anyone knows about the American cartoon or American commercials, TV commercials that eat this cereal. Or if you mix these colors together with a bird like this, yes. It looks like that crazy thing.
Yeah, Tucano.
Tucano, okay. Okay, so next up,
it's a highly personal, identification, right? For you, for a Canadian, I would probably identify that with the little smaller one.
Yeah, but the colors, no?
That's more, the hundreds.
The colors,
but that's a good one.
If you mix the colors with the bird. Okay. Next one will be more interesting. So, what are the functionalities that you can get with hybridization? We've already heard a few things from the previous talks. We heard about microwave to optical transduction. We heard about quantum information transfer over distance or coherent coupling of spins at distance. Another thing that I think my student Ivan will talk about is the ability to break effective symmetries in a model, provided you hybridize single Magnon modes with two Magnon bound states, and that allows you to generate a topologically non-trivial phase, which might have an edge mode that you can control. Are there other interesting functionalities that we have beyond these ones here? Or is it all about transduction, sort of moving microwave to optical frequencies? For you, what is the most important application? Yeah.
Well, I will be discussing a little bit of, it's along the lines of like transduction, but Magnons are like potentially very good for entangling and mediated coupling between different qubits or things of that sort.
Are you thinking specifically of hybridizing with localized spin qubits?
That's correct.
Charge qubits? Yeah.
With either like Skyrman qubits or nitrogen vacancy centers. So that's one example. There's
idea here.
So I'm interested in this perspective of breaking symmetries and or induce topologically non-trivial phases with Magnons.
Yeah.
Because we kind of know or are a bit more advanced in this field when we deal with electronic states.
Right.
But with Magnons, what do you have in mind specifically when you connect Magnons with breaking symmetries to create topological, non-trivial topology?
Okay, so there's a lot of work that's been done before us on this topic, but just loosely you can think of mapping the system of spin flip excitations in an Ising magnet. So you flip one out of n spins and you create a little excitation at a particular point in space. You can think of flipping that spin at any point in space. That's like creating a little particle at one point in space. Yeah. And then if you flip two neighboring spins, this is a two-magnon bound state if you have the right type of Ising interaction, that creates another type of particle. And that type of particle can be created at any point in space as well. So you can think of creating two different types of particles, particle A or particle B, one spin flip or two spin flips at any point in space. And then you can think of interactions. So if you can do that, and then you introduce, say, some non-Ising terms, those allow mobility, or you hybridize the localized states to create delocalized Bloch waves that allow you to hop with your excitation from one site to the next, one site to the next. And then you can also have interactions that don't conserve the total spin, that might take you from one type of excitation, single spin flip, to another type of excitation, two spin flips, if you don't conserve the total spin. Okay, so now you have interactions that allow you to create an effective lattice model where you have these particles, these excitations, single spin flips, that can be at any point in space, and they can hop from one point to the next, or they can convert from one type of particle to the next. It's kind of like thinking of a system of electrons in a crystal with a little unit cell that might have three different atoms. One for two spins flipped along the x direction, one for two spins flipped along the y direction, and one for a single spin flipped at this site. Okay, so if you have three sites and you have hopping between all three sites, you can think of inducing a kind of phase or a gauge term, a little like effective. You have an effective magnetic field for that particle. And that allows you to create a kind of staggered flux phase that's very similar to the Haldane model, which you're probably familiar with. And then you can induce a topologically non-trivial band of excitations. That wouldn't have been possible if you didn't have all of these systems or all of these interactions that hybridize the different degrees of freedom. Okay, so that's an example, or that's the example that I meant when I was thinking of that. But that's one example where, so initially, if you don't have a term that breaks spin conservation, so in this case you need a Jalachinsky-Moria interaction in the right way, then you cannot induce this topologically non-trivial phase. So you end up with no effective gauge potential. So you end up with no extra phase on the effective particles that hop from one site to the next. And I'm sure there are many other examples that I don't know of yet, where you can map your system of excitations, the system of Magnons, onto an effective other model that has some special symmetries when you turn off this hybridization, but when you turn it on, maybe break those symmetries, and you allow new functionalities. If anyone in the audience knows of other examples like that, that would be really interesting to hear about. Is there a microphone?
So I think also about this break symmetry stuff, you can also use like spin polarized current to like modify the dispersion relation so you can have like different effects depending on the polarization of the current. Mm-hmm. But yeah, going to the previous idea of mixed states, can we also have some like hybrid Magnons by just coupling the Magnon with the anti-Magnon?
Coupling a Magnon with an anti-Magnon?
Yes.
So you're thinking of a chiral Magnon or something? that would annihilate?
I think like
Sure.
you can create, for example, cavity and then since you propagate the spin waves, it is the magnon, but where it interacts with current distribution or Jaloushinsky-Moriah interaction, you can have interaction between the magnon with the antimagnon that is created in that specific part. So can you have interaction like this? And
maybe you're thinking of a specific kind of situation where you have like a kind of chiral domain wall or something.
Yeah, like
and
like
you
a
have one
cavity
chirality and another, and if they come together, then they annihilate.
Yeah, or resonate. You can also like create resonance. For the current. And also the Jaloushinsky, because then the polarization can play a role in these things. I mean, polarization for current and the D sign for the Jaloushinsky-Moriah interaction.
Okay.
But I mean, I'm just wondering if these can be called also like hybrid magnon.
I don't see why not. If you have two different flavors of magnon and you're hybridizing them, I think if they have different characteristics, like a different group velocity or something, and then you're using them to change the dispersion of the composite particle, I think that's an interesting thing. I think Michael already talked about that.
Okay.
There's an idea at the back, Yaroslav. Oh, sorry, you want to continue?
Yeah, just wanted to comment on that. So the easiest example is a Diamond-Ashbach mode, which can only go one way. So you can take a thin film. So there would be one Diamond-Ashbach mode going up, right, let's say, and on the down it would be going left. But if you make it very thin, they hybridize. But then what happens is totally, well, I cannot say it's uninteresting. I will be actually talking about it a little bit tomorrow. But what happens is basically the resulting mode, as you would expect, is not chiral anymore. And so there are still some things which remain, but I mean, this chirality is lost because of the
Can you tune the group velocity though?
Oh, sorry.
Can you tune the group velocity? Because you've got one mode that has velocity in one direction, another mode that has a velocity in the other direction. If you have a balanced superposition, they should stop. And if you have an imbalanced superposition, it should go one way or the other. No way.
Yeah, but you cannot anymore talk about just two group velocities, right? It would be something which is not even a running wave.
Are you breaking translational invariance in one direction though? I thought you're describing a situation where you have translational invariance, say in the x direction.
Yes.
But where you have a finite strip.
Yes.
And then if you hybridize two modes that still have translational invariance in the x direction, you're saying they're not traveling wave modes anymore?
Yeah, I cannot answer that now. We haven't looked at that. I don't know. But what I'm pretty sure about, if you just start looking at the field profile, right? For a surface mode, it just decays in the bulk very quickly. But if you have a thin film, it doesn't decay in the bulk anymore. And in some limit, it's just, doesn't decay at all. So it's homogeneous over the film. And then you probably still ask what the group velocity is. I don't know, to be honest.
Okay.
But definitely it's not something which is chiral. It's something which exists everywhere.
Yeah. Okay.
So regarding the functionality, I definitely get the transduction part, and I do like the break symmetries. The fact that in these magnetic systems you have the time reversal automatically broken and get non-reciprocities. I think that's probably the most useful aspect of hybrid Magnons. I'm not so sure that I see, the information transfer over distances and coherent long-range coupling. Because after all, the lifetime of Magnons are, at least in the quantum world, pretty atrocious, mostly. And
but does it have to be like that? Is that I agree with, I mean, current state of the art, it seems true, but does it have to be like that? Is there a fundamental reason that it can't get better in the future?
Well, I mean, it's probably for the same reason that we like them for transduction, that they like to couple to all kind of things, right? And so I'm a little bit more skeptical that that's where the journey really goes. Having said that, as far as I can tell, most of the hybrid Magnon modes really looks at stationary modes, right? Like a Kittel mode or something. And very little has been done with propagating Magnons. And I think certainly there's, you know, lots of interesting things that can happen there.
Okay. Oh, yeah.
Wait.
They also act as sensors. I'm not sure if it follows in the
Oh no, that's a very good point. I didn't even think of this, but absolutely they can be sensors. And when you say sensors, do you think of sensing magnetic fields, or you want to sense something else like gravitational waves?
It depends on the situation. In the example Dennis mentioned, in the axion detection, they're there to help or assist the detection of a more elusive state of matter.
Yeah, that makes sense. So are there unsolved questions about sensing with Magnons that we know of? I'll get to that in a second. Maybe we should wait for the unsolved questions slide. Okay, I'll go to the next quiz. Oh no, there's a quick, Denise.
I think one more functionality that I saw recently being presented at March meeting was using the number of occupancy of the Magnon, namely 0 and 1, as a qubit. So of course that it requires you to go to super low temperature, but I know that there are like some people already like looking into this direction.
Yeah.
And also trying to mimic like whatever happens at the photonic realm. So like different Magnon chiralities combined with Magnon occupancy and
so you can have a kind of mimetics of other technologies that you've already seen for photons, or some other degree of freedom has worked, and then these are another form of bosonic excitation that maybe you can manipulate in a new way. Yeah. So what would be good examples other than communication? I mean, communication maybe is not good. Sensing, I guess, interferometry.
Yeah.
Okay, next quiz question. This is another Brazilian animal. This one is maybe easier, more universal. Can you think of a Brazilian animal that's a hybrid between those two things? Some would say it's a lazy animal. It's not a zebra. It's not a zebra. Don't focus on the shirt. Sloth. So unfortunately, I think this is an AI-generated photo because the hand doesn't quite match. But you see, you see the resemblance. Those two. Okay. It's okay? All right. So now, what are the open science and technology questions for Magnons? I think this is, for me, is the hardest question. I guess the first question that I had, which I don't even know how to address, is if there are fundamental limits or practical limits that make it impossible to do coherent information transfer. To Axel's point, Magnons are usually short-lived. Are there fundamental reasons for that? Or are these just practical limits that we can overcome in different materials and doing different processing or by using clever tricks? Does anyone know of a fundamental limit or something that might be almost something that you couldn't overcome?
Well, total number of magnons are not conserved. So by definition, there's always going to be some like induced lifetime due to scattering and 3-magnon process.
Right.
So in that sense, there are fundamental limits, but I don't think we're even close to those currently.
So you think even for a perfectly dilute system, though, if you have a perfect Heisenberg ferromagnet, you can make 1 magnon. But you're thinking about the situation where you're making multiple magnons.
Well, at low temperatures, I think you can perhaps suppress these 3-magnon processes, but like we cannot define chemical potential because number of magnons are not conserved. So since number of magnons not conserved, they're going to have like a finite lifetime.
So it is conserved for 0 or 1, right?
What do you mean 0 and 1?
If you have a perfect Heisenberg ferromagnet, then you can solve for the exact eigenstates.
Well, but if I have a perfect like Heisenberg, then I think we have then magnons would be like pretty awesome, pretty good.
But you're saying there's never a perfect Heisenberg ferromagnet.
That's correct.
Yaroslav might have something to say about this too.
Right, so we're going into semantics again, right? But
Okay.
let's see. So S squared is constant, which means any magnetic system is fundamentally nonlinear. If it's fundamentally nonlinear, there are always magnon-magnon processes. Now you can say, fine, let's take a many-body system and solve it, and then talk not about magnons which we understand as, the excitation of the, macrospin, but these solutions of the total nonlinear problem. And those, of course, would not be interacting and probably would be stable. But then the question is whether we are really talking about magnons, because if we are couple them to the external world, we are coupling everything to the macrospin. So in this sense, I think that's a totally fair statement that there is always many body processes which limit the coherence unless we find some way of coupling something to the many body states.
Okay. I think I was okay. I think I was making a statement about the exact beta ansatz solution. If you go, just for a single excitation, everything is fine. It doesn't matter if it's a boson or what, because there's only one of them. And then I guess it's consistent with what you're saying. Okay, I see.
Yeah.
Thank you. Okay, so what are the practical limits to coherence? Maybe just the fact that magnons are not really bosonic and that they interact. What are the practical limits to strong coupling? I wrote Q equals question mark, but that's coupled to the question about coherence as well. So is there a fundamental limit to strong coupling? I guess the exchange can't be larger than the orbital energy of a single atom. I don't know if that is a comment here.
Well, I don't think there are practical limits to strong coupling, because we've seen strong coupling in many instances with microwave photons, with phonons, with qubits, what have you. And I mean, you can have cooperativities that are really high. You can even get to like in the ultra strong coupling regime.
Right. So you're saying that if there is a limit, it's so large that it doesn't really matter. Is that right?
As far as I can tell.
Yeah. Okay. So what? But given that the cooperativities are high in some cases, why is it that people still don't see these effects like vacuum Rabi oscillations for magnetic systems? This is maybe a practical question. So it's a yeah. Okay, so maybe it's just practical limits right now, and we don't have to worry about fundamental limits, but there are practical issues still to resolve. And then I wrote spatial limit to information transfer, and I've forgotten what I meant by that. Oh yeah, so how far could you imagine sending information with a Magnon pulse? Or maybe you just don't want to do that because Axel doesn't like Magnons. so if you don't want to send information, maybe it's a different story, but if you wanted to send information from one place to another, either quantum or classical with a Magnon excitation, is there some basic limit to how far you can send that information? Yeah, do you know?
Well, I mean, the longest propagation distances that we've seen, like super clean YIG could be millimeters, maybe centimeters.
Okay.
But for most practical things, it's probably more like tens to maybe hundreds of micrometers, you know, if you're thinking of thin film devices.
And what sets the limit? Is it
the
geometry
lifetime,
of the device?
you know?
Yeah, the
lifetime and the
then
relatively low group velocity.
what about, say, demagnetization corrections? Do they not matter? So the shape of your sample or a geometry for a finite sample, does it come into affect the lifetime?
I certainly don't see how it makes it better.
Yeah. But is it relevant, or is this irrelevant for the most of the systems that people are looking at now?
Okay.
So let's say.
Yeah, some thoughts over there.
Well, maybe if you have some kind of way to compensate the dumping losses of the system, you can be indefinitely long as you can.
Right.
So
So you think maybe an error correction scheme that's loss resistant for Magnons?
Yeah. Because I mean, because you lose your angular momentum with time as well with the distance. But if you somehow you can pushing back, let's say, the losses, the coherence of this information, the spin information, could stay alive, and the only thing that you need to push up is this a little bit of angular momentum that has been lost. So, well, I don't know exactly. Well, there is a few ways maybe, like injecting by few other things, but that's one way, I would say.
Okay.
So in my head, it could be indefinitely long, but.
Okay. No, I think that's true. If you have a good error correction scheme, people have demonstrated it for microwave photons now.
Yeah.
Why not for Magnons as well eventually? I don't see an ultimate reason why not, right?
Yeah. Well, the hard part is to make a YIG with 10 meters, right? long. This is a little bit hard.
Yeah, so that's practical. Or, okay, so it just breaks, or, okay, you get defects. And then I think, okay, I wrote highly system dependent, or are there fundamental issues? I guess that's a continuing question that I have in my head. You know, it seems like most of the things that we discuss are very system dependent, so it depends on whether you're using YIG or some other organic magnetic system. You're going to get slightly different questions and slightly different answers. But are there overarching fundamental issues? And I guess we've touched on a few of those a little bit. Things like losing excitations to 2 Magnon, 3 Magnon modes. So those have been touched on. So are there more? Are there more open science questions that we have to answer as a community next? Or it could be technology questions. So what would be a question about how to practically use these things? Do we need magnetic memory again? Or are we happy with flash? Are there situations where we still need non-volatile magnetic memory, or is this not an issue anymore for the field? Do we need magnetic quantum memory? I think we do need magnetic quantum memory, but it probably doesn't exist in a ferromagnet or antiferromagnet. It probably exists in individual atoms or in dopants in some crystal. But I could be wrong. It could be that we need collective motes of some ordered system. Okay, I'm going to the next quiz question. This one is hard. So what kind of animal would you think about? It's hard, remember, so there's some misdirection. Someone said flamingo. It's a good guess. It's not a flamingo. I mean, it could be a flamingo, but it's not. It's something else. It has the same color as a flamingo. Is there an idea in the back? Just shout out anything that comes to mind. It's very Brazilian. Sorry? Okay. So everyone's familiar with the pink dolphin in the Amazon? Okay, good. So here, I'm not sure what to say. I tried to think, I didn't have a lot of time. I tried to think a little bit about what experiments there might be, but I haven't got a really good idea myself about what experiments we need as a community to do whatever it is we want to do. So if people have ideas, or if people are working on ideas for the next experiment, maybe you can tell the crowd. Oh, or I could phrase it another way. It doesn't have to be anything that you're working on or that you're thinking about. It can be anything that you think would answer a really important question. So some result that might be a very challenging experiment, very, very hard to do, but is there something that could answer an important question that we don't know the answer to? There's an idea up at the back.
So actually we use this known, the scattering type of near field optical microscopy for probing and imaging polaritons, Phonos polaritons and so on. Yeah. I don't know in detail how is the difficult to extend the energy range for probing hybrid polaritons, but I don't think it's so difficult to do that.
Can you do it spin resolved with polarized light?
Yeah. Actually, we extend our energy for the terahertz.
Terahertz, okay.
So maybe.
Okay.
We can do it.
Can you generate a particular spin orientation for your polariton? So with a particular spin polarized exciton?
There is few places around the world that it's possible to couple this experiment with magnetic field. So.
Okay.
Maybe.
Okay. Miroslav.
Right. I maybe just do some random things.
Yeah.
Okay. So one thing is indeed coupling anything to terahertz radiation. We could think about terahertz cavities. We can think about something else. It's clearly underdeveloped, and that's a big problem because we have a lot of things in the terahertz range, including antiferromagnetic magnons, pretty much in every material.
Right.
Now, specifically for antiferromagnetic magnets, not necessarily terahertz. I mean, in late materials, they could go below terahertz.
Yeah.
Still, it would be great to have some way of detecting them. I mean, right now, the mainstream thing is basically this neutron scattering experiments, which you need a facility and you need a bulk sample.
Yeah.
It would be great to have it for
surface,
or for layers, for atomic layers, and then you need something else, and that's a problem. There is, of course, anti-magnetic spintronics, but then you don't. That's indirect. So I think that's also something which is underexplored.
Okay.
And maybe the last I mentioned before going to something else, I think. Going to strong coupling would be great. And now by strong, I really mean like ultra strong compared to the, I don't know, frequency of the cavity. Because then there would be different effects which we don't quite understand. We can learn from other fields, like optomechanics would be one where people really try to explore that. I'm pretty sure there are other fields we can learn something from, but in Magnonics we don't have that.
Can I ask a question connected to the first statement about terahertz?
Yeah.
So you phrased it as a problem of being able to detect magnons, because magnons have a resonance in the terahertz regime. Is that right? So, but can you turn it around and say magnons are probably a very good detector? They're a sink for energy in the terahertz regime. And
yeah, you can also indeed do that because that's indeed terahertz radiation. There is a lot of terahertz radiation, and we don't know what to do with that.
Right.
Maybe we can do something useful with it. But the problem is, I mean, if you have antiferromagnetic magnons as detector, you need to find some way of reading them out,
right?
Which is by itself a problem.
Exactly.
So I agree that that's something that's basically a collection of things we should be thinking about together.
Yeah.
But yeah.
So okay. So then the trick would be, in that scenario, would be finding another detector for the antiferromagnetic magnons.
For example,
the absorption of energy is not sufficient if you want like a single photon terahertz detector. Yeah. Okay.
Maybe it's a dumb quest, but it's more because today we talk a lot about kind of setup, like spin center, stuff like that in the Magnon sense.
Yeah.
And that's looked to me very familiar, very similar with the setup that happened in Kondo effect.
Yeah.
In some sense. So, and that's my question. It's not an answer, sorry. But I can make some experimental stuff that coupling this Magnon with this pseudo state of the Kondo effect, or something like that.
So you're saying maybe we can learn from all of the many experiments that were done on the Kondo effect? Is that what you're suggesting?
I'm asking.
I mean, this is for the room then. So I'm not an experimentalist, so it's difficult for me to say specifically.
Okay.
And I am not an expert on the Kondo effect. I know what it is, but I don't have a detailed understanding that allows me to say.
It's because it's kind of a pseudo state, right? When it happened, the Kondo effect.
It's a pseudo state or a hybrid. You think it's a hybrid state because it's basically a cloud of.
Yeah,
singlets.
but because in the list of states they have a peak that they behaves like a state, right? A pseudo state. I'm asking if I can hybridize the Magnon with these states.
Oh, you want to hybridize with the Kondo cloud. So if you have an impurity and you have some kind of reservoir of electrons, and the reservoir of electrons have an exchange with the impurity, they form this Kondo cloud. Yeah. And then your Magnon comes by and it sort of hybridizes somehow with the Kondo cloud to distort it or change the characteristics of the Kondo effect. Yeah, I mean, why not? Sounds plausible. Okay. But would it be interesting?
I'll give you an example. I don't know if you know CR-SBR material as a semiconductor to the antiferromagnetic material. And you can use extons to probe Magnon because it's coupled. Yeah. So you can perform time-resolved photoluminescence. You can do pump probe. And there is some oscillations. And the frequency of this oscillation are the frequency of Magnons. So you can use, you can see these Magnons by performing this kind of. But it's a special case for this material.
Oh, that's very interesting.
Yeah.
Okay,
I will present my talk.
Okay. So is it basically that you go between a bright and a dark exciton?
Yeah.
So if I have a spin here that is coupling to another magnetic system, it trades its excitation.
The main issue is because this material, when it's on ferromagnetic or antiferromagnetic, they have different energy of extons. So this is because when it's antiferromagnetic, you cannot have tunneling. They have a coupling between layers. One layer is implant the magnetism, and it's ferromagnetic, antiferromagnetic. It's another direction, so it cannot have tunneling. Okay. if you have you put magnetic field, you can have ferromagnet induced by magnetic field, so you can have tunneling. You have a hybridization between the layers. You can change the energy of extons. And as you have this, you can use a small magnet on a cryostat with 0.2 Tesla, a very small field, and you can use pump probe technique, and you can see this oscillation in the PL, in the photoluminescence.
Okay.
Well, I can explain better.
It's more some tunneling magnetoresistive effect that depends on the presence of
It's more
oxidants?
because you can change these spin waves because of this coupling of layers in this special material.
Okay.
Yes, it's a Nature paper. I can give you.
It sounds really interesting.
It's very interesting.
Okay. I think one of the good things about this session is that we learn kind of what everyone is doing in the room. So if people have stuff they want to advertise, it's probably a good time.
Yeah. So also about experiments in hybrid Magnons. So still in the thing I talk about, like STT effect. So could you also like you have a stripe and then you just add current in the center of this material, and then like if you measure the spin waves going through it, and you can measure actually the amplitude of the resonance in the center. I'm not sure about like measurements because I'm not experimentalist, but you can, I mean, from simulations at least you can see that you have resonance in some, depending on the size of your cavity, for some current effects, for some current values. So if you measure that, you can actually see these interaction between magnons and anti-magnons that could generate resonance. So,
okay.
I mean, is it possible to do an experiment? Because there's also a problem of like how much current you can add, and because it will also generate thermal effects, which is not good for like studying current magnons. So.
But that sounds like an interesting thing to bring up at a coffee break, or if people have ideas about how to do the experiment. But yeah, that sounds like an interesting thing to bring up with the experimentalists at a coffee break.
Okay.
Oh, did you want to ask a question? No. I will go to the next quiz question, I think. It's another Brazilian animal. Sorry? Oh, I don't know the Portuguese names.
Armadillo.
Say it again? I couldn't hear. Camandua?
Anteater.
Oh, that's very close, but no. So very, very close. Yeah, I realized it could be confused. It's another one.
Can it be smaller? Because it's,
it's not as big as a rhinoceros, the animal. It's smaller than a rhinoceros and maybe about the size of a vacuum cleaner.
Armadillo?
Armadillo, no. There's another one. When I show you the picture, you'll agree. No one knows? Anteater has been called, and it's not what I had in mind. I understand that it could work, although less rhinoceros-like. This one is more rhinoceros-like on the bottom, more vacuum-like in the nose. Not an anteater, though. Is there an idea? This one.
Oh, my God, yeah.
Tapir. It's the Brazilian tapir, specifically. Okay.
So do you know the name of that in Portuguese?
No. What is it?
Anta.
Anta. And does that have another meaning? Is it?
It's a slang for someone who is pretty dumb.
Oh, I'm sorry. I wasn't trying to suggest anything. I didn't know. Totally oblivious. That's the last one, though. But it's not supposed to be I'm ending on an insult. This is also the last question. And it is, what theory do we need? So if you're an experimentalist and you wish that you had some theoretical explanation for some phenomenon, or if you're a theorist and you realize that there's some pressing need for some understanding in some area, what area is it? This is the hardest thing, to answer the questions or to ask the questions that haven't been asked or aren't being asked. Or even if there's a question that everyone knows should be asked and no one knows the answer. think everyone is tired at this point. Yeah, Denise, go for it.
So this is kind of more or less aligned to the previous points we discussed, which is like to have coherent magnons, we need like longer lifetime, large like couplings and etc. So it's not really like development of new theory, but rather exploring the theory that's already developed to look for how to improve the coherence of like magnonic systems in kind of general. And then interesting approaches involve use of machine learning, optimization algorithms, and artificial intelligence just to understand what are the best avenues and routes to look for.
Right. Yeah. No, I think I agree. Yaroslav, and then Michael.
So I actually work with experimentalists quite a lot, and I know what questions they ask. Right. Please. So what they ask is, if I kind of summarize it on a meta level without going into details, right? What experiments can they do to see magnons?
Yeah.
With the conditioned on the tools they have.
Right.
Because clearly somebody, who is doing, optics is not suddenly go and, couple a X-sphere to a qubit, right? I mean, but conditioned of what they have, what are possible experiments, and what can be observed in these experiments, which would
with limited resources. So find ways to detect magnons with existing experimental technologies or methods.
Exactly, and what information can be precisely extracted.
Yeah. Okay. Very good. And Michael had his hand up.
Yeah, I think that what I also hear often in this area is sort of similar to the superconducting case. So in the semiconductor community, there's been 50 years of work on the sources of noise and the two-level systems you have, because this was technologically relevant. In the case of superconducting qubits, there's just very primitive levels of understanding of what's actually going on there. And the situation for magnetic systems is even worse. Right. So it's how do you connect the magical Gilbert damping factor to actual microscopic features of the magnets? That's in my opinion, the biggest open question for magnons right now.
Yeah, excellent.
Well, I would also say if we really want to push magnons to the quantum regime, how do we have to worry about things in their dynamics that is different once you get there? Does the damping, for example, change? If we are interested in using propagating magnons, how do we think about things like shot noise and things? Those are some of the things that go through my mind.
Yeah, no, so I think there are some other things that are connected to these questions that have been raised about coherence and dissipation and damping that I worry about a lot. So one issue is that we often sort of take the mechanisms of decoherence or information loss to be exactly the same as the mechanisms for energy loss. But this is not necessarily the case. So decoherence is a loss of information. It's not necessarily a loss of energy. So there are situations that you can construct where, despite the fact that you might lose some number of magnetic excitations, you can still preserve the information. Error correction is an example. So you can encode in a larger space and then detect the fact that you've lost one excitation and then correct for it if you have a good encoding. And so that suggests that the impression that many have, which is that magnons are just very short-lived objects and may not ever be useful for information transfer, may not be correct long-term. So if we can think of ways of encoding better and protecting information better, despite the fact that energy loss mechanisms are very difficult to deal with, we can just accept that some energy will be lost, but that the information can be preserved. Yeah, well, these are really good points. Yeah, I mean, do we have to go for the whole hour and a half, Carlos? Because, if there are more, yeah, sorry.
Oh, sorry. I was just going to ask or make a very specific point, perhaps, of things that have come up in experiment and theory. So when doing experiment, it's great to see sometimes people have done something in theory and we're like, oh, we can do this.
Yeah.
And that is great. But with especially hybrid magnonics or cavity magnonics specifically, there is a lot of things where we can do things, but they are not always explained in the terms of the things that we can actually do. And someone pointed out earlier or commented on these exceptional points, for example.
Right.
And in the experiments, we see loads of those types of things. And the question from a theory standpoint to me, for example, and is that what we actually see? Because the theory is done, if you write a set of coupled equations and you give us a set of conditions, you can say this is what you would see.
Right.
But in terms of experiment, the questions are, what does that actually mean in terms of the experimental conditions, right? Is a damping term or an imaginary thing or a lossy system? Fair enough. But in terms of the experiment, what do we actually do to make that happen? Do you need more losses in the magnetic material? Do you need, a cavity that is, we talk about good quality factors in those systems. Do you need something? Is really translating the same language, having the same language or having more.
Yeah, I think it probably comes back to what Jaroslav was saying about how, the key question is always what you can know with the tools that you have and what you can determine to be the boundaries of your understanding. And in some areas, people know the systematics so well. So in high energy experiment, very often they know the systematics of their detectors so well that they can control them to an extreme degree of precision, but that's not always true in our field, right? So it's very often the case that we have a kind of messy apparatus and we're doing our best to understand with an effective model, which is not exact. And then your comment, I think, is that you would like to see more boundaries or more understanding of how far you can push the interpretation. Yeah, and that's a burden for the theorists for sure. That we should do more probably to understand the limitations of the theory. Or if it's an effective model, we should say, okay, this effective model realizes this behavior under these specific conditions and not beyond them necessarily. Yeah, that's a good point. Okay, I guess if there are no more questions, thank you for joining the session, and you did well on the quiz.
So thank you, Bill. You set the standards very high. So the next one, that was my idea. You know Bill very well. So I actually didn't introduce him, but we know each other for a long time. He started as a graduate student in Basel when I was still there. I never left, actually. 2002, right? When you started, I think. Yeah. So